measures of spread. Fran has exam scores of 71, 81, 91. Sandy has exam scores of 80, 81, 82. Both students have the same mean and median, but Fran's scores are more spread out. So the mean and median measures center or central tendency, and as long as also the mode and the mid-range, they all measure central tendency. But we also can compute some statistics that measure how spread out the data is, and we have already computed the range and the interquartile range in another exercise. So the range is the largest minus the smallest. So the range for Fran would be 91 minus 71, which is 20, and the range for Sandy, 82 minus 80 is 2. So the range also is a clue that these are spread out, that Fran's scores are more spread out. But there's some other measures of spread that I want to go over now, and actually they're more important than the range and the interquartile range. There's some strong theorems relating to the variance and the standard deviation, the relationship between the sample variance and the population variance, and also the standard deviation and the population standard deviation. So those are important measures of spread. And we'll start out with the variance. And the variance is represented, the sample variance is represented by S squared. It's given by this formula here. Again, capital sigma, Greek letter capital sigma means sum. And what the sum is, k goes from 1 to n. You might see some, it doesn't have to be a k here. It could be, oftentimes with the summation, sigma notation, they use I or j or k. I'm using k. I think k shows up on the screen better than an I or a j. It's easier to see it on the screen, so I'm using k. But the summation is k goes from 1 to n. Sk minus x bar is the sample mean, the quantity squared over n minus 1. So this formula sort of tells us the order of operations. You want to first do what's inside parentheses, each score minus the mean, and before you can even do that, you have to find out what the mean is. So find out the mean, and then each score minus the mean, and then do the exponent, square it, and then add them up, and then divide. Last thing you do, divide by n minus 1. So this is the formula for the sample variance. The population variance is almost the same, except you're dividing by n, and but we're mostly going to be working with the sample variance. Okay, so let's go back to my previous page here. We're going to consider these exam scores here. We have 12 exam scores of 80, 88, 28, 91, 61, 88, 83, 59, 72, 78, 89, 82. So the first thing we had previously computed the mean, 76.9166667, and anyway, the first exam score on this list here was 80. So x1 is going to be 80. We want to compute, again, we're following the order of operations, 80 minus the mean. So 80 minus the mean, which is 76.9166667. And if we do that subtraction, we'll get 3.0 8 and a bunch of 3's. 3, 3, repeating 3. I'll put a bar over 3. There's more room down here. 3.08333333. and actually the 3's go on. Okay, so and then we want to square this number. So 3.08 and repeating 3's, and then square it. So with this many digits, I think with the smaller data sets, I think you should be able to do this by hand, but this is a pretty large data set, so I'm going to put these in a calculator here. So it's 3.08333. It's repeating 3's, and then squared. I get, try it again, 3.083 squared. You get 9.5 something. 9.5069 and repeating 4's. And then you do that for each data. So I did that for the score of 80, but you want to do that the same thing for each data. And okay, so then we'll end up with. So this is for the first exam score, but then you do the same thing for each of these exam scores. So each score minus the mean. Some of these will be negative, some of them will be positive. But when you square that, negative times negative is positive, positive times positive is positive. So this last column will all be positive. The middle column should come up pretty close to 0. Now this is a little bit off from 0 because of rounding errors. If there's no rounding errors, then it should be exactly 0. For example, for the first deviation from the mean, 3.083333333, I only included 9 digits after the decimal, but these 3's keep on going out to infinity. You know, I mean, this may not look like a rounded number to you, but it is a rounded number, and all these are rounded numbers here. So our middle column was a little bit off, but even with rounding, it should be pretty close to 0. If there's no rounding, then it should be exactly 0. And then when we square these, we'll get this column total here, and then this is what we use to compute the variance. So it's the last column total, this numerator here. The sum as k goes from 1 to n, each score minus the mean squared. So the sum of the last column, which is 3746.91 and repeating 6's. And we have 12 scores, so at 12 minus 1, which is 11. 3746.916666 divided by 11. See what we get for that. For when you have this many digits, I would use a calculator. Some of the smaller data sets you should be able to do by hand. Divided by 11. About 340.6287878. Okay. Okay. So that's the variance. And again, variance is important. There's some strong theorems about the variance. Probably. An even more important measure of spread is the standard deviation, which is the square root of the variance. So that's represented by the sample variance, represented by the letter S. Square root of the variance, which would be square root of 340.6287878, and that's equal to second square root, about 18.45613.144. So standard deviation. One of the theorems about the standard deviation is Chebyshev theorem, part 2. It says at least 75% of the data is within 2 standard deviations of the mean. So, so if we round this off, let's say this is approximately 18. So 2 standard deviations below the mean, 77 minus 18 is 41. 2 standard deviations above the mean, 77 plus 18 is 113. And Chebyshev theorem part 2 says that at least 75% of these scores should be between 41 and 113. And in fact, 11 out of 12, if you look at the original data, 11 out of the 12 scores are between those numbers. So we have the only score that's not between 41 and 113 is the 28. 28 is the low one. The rest are all in between. So anyway, so that's one of the reasons the standard deviation is important. And there's some other theorems too that will use for the standard deviation. Now, it's going back to this this computation I did earlier for the variance. We said that this middle column should be equal to 0. That's the sum of the deviations from the mean should equal 0 if we did everything correctly. So you can use that as a check. And if there's rounding, it might be a little bit different from 0. We had some rounded numbers here. But anyway, we'll do a proof. This is a proof that for any data set, the second column total is always 0. In other words, the sum as k goes from 1 to n of each score minus the mean has to always equal 0, no matter what. So we're going to start out with the left side and try to manipulate it to get the right side of the equal sign. So we have start with the sum as k goes from 1 to n, each score minus the mean. So we can write this as x1 minus the mean plus x2 minus the mean plus etc. 3 dots for etc. plus the last score minus the mean, xn minus the mean. Okay, and then this is by definition of sigma. And then we can rearrange these. The order doesn't matter for addition, and also it doesn't. If you take the sign with you, you can treat subtraction like an addition, and the order doesn't matter for that either. So, so we can put the x1, x2, etc. together. x1 plus x2 plus etc. plus xn, and minus x bar minus x bar minus etc. minus x bar. This is because it's by this commutative associative properties of addition. It says that order doesn't matter for addition. 3 plus 4 is the same as 4 plus 3. 3 plus negative 4 is the same as negative 4 plus 3. Associative, by the commutative associative properties of addition. But it just says that the order doesn't matter for addition. Okay, so then we can rewrite this first part is using sigma notation again. Summation k equal 1 to n of each score. Minus x bar, minus x bar, minus dot dot dot, minus x bar. And this is by definition of sigma. And then we can combine these. These are we're subtracting x bar n times, so we can write that as n times x bar. So summation k equal 1 to n xk minus n times x bar. And that's by because multiplication can represent repeated addition. Multiplication can represent repeated addition. Okay, so then get a different page here. Okay, so then we can write this as leave the first part the same. We can use the definition of x bar to write this as the summation k equal 1 to n xk over n. This is by definition of x bar. That's the definition of the sample mean. Of x bar. Okay, and then we can cancel the n's. So we have n on top and bottom. If you want, you can put the n over 1, and then cross-cancel the n's. So this is the summation k equal 1 to n xk minus summation k equal 1 to n xk. That's by the rules for multiplying fractions. And then that's equal to 0. And any expression minus itself is 0. That's because a number minus itself is 0. Okay, so that completes the proof. So we just proved that for any data set, this column total should be 0, and if it's not equal to 0, it might be a little bit off because of rounding, or if it's more than a little bit off, maybe you might want to check to make sure you have the right mean, using the right mean. And that concludes this presentation.